we're going to start this again. We're going to look at numbers 2, 7, and 1 on the molarity practice sheet. So for number 1, you're told that you have an 8.6 molar iron 2 chloride solution. We want to know if it's saturated or not. Or has been brought to my attention since I seem to be lacking, well, I've been whistling if I only had a brain for the last hour. It's bound to have an effect. You're told that you have an 8.6 molar iron 2 chloride solution. We want to know if this thing is saturated. So anyway, we have 8.6 molar iron 2 chloride. We want to know if it's saturated or not. So one of the easiest things to do is say, well, what's the molarity of a saturated solution? And then compare the two. So at 10 degrees, we know that, well, okay, let's write this down, shall we? If we wanted to figure out the molarity of a saturated solution, we'd be looking at how many moles per unit volume, per liter, we would have in a saturated solution. What we know about iron 2 chloride is that at the temperature specified, which is 10 Celsius, so at 10 Celsius, we can dissolve 59 grams of iron 2 chloride in every 100.0 grams of water. Okay, that's reasonable. So if I give you 100 grams of water, which we all know is about 100 milliliters of water, we're going to be able to dissolve 59 grams of iron 2 chloride in it. Well, what we'd really like to know is how many moles of iron 2 chloride that actually is. So we're going to start this as a second factor label. There would be a way to do it all in one, but it's confusing because it just is. So we're going to start it off as a second factor label. 59 grams iron 2 chloride. Iron 2 chloride has a mass of 126.75 grams. She said with a question because, yes, okay, not 5775. In 1 mole. So in that 100 grams of water, how many moles of iron 2 chloride do we have? We get 0.46548 blah 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 moles of iron 2 chloride. Okay. So what's the molarity of that saturated solution? Well, the molarity of that saturated solution is 0.46548, on and on and on, moles of iron 2 chloride in how much solution? It's not a whole liter. This was in about 100 milliliters of water. Now, here's the fudge factor we're using. We're saying, yeah, it was 100 milliliters of water. Okay, we have 100 milliliters of solution. We would actually have slightly more than that in volume. If you were doing serious quantitative chemistry, this would break you. Like, this would cause you enough of an error and enough of a problem. To get the idea, we can do this. We're going to say it's in about 1 liter of solution, or 0.1 liter of solution. Because 100 milliliters, of course, is 0.1 liters. So now we get the molarity of a saturated solution is 4.65, etc. If we have 2 sig figs to play with, we would say this is a 4.6 molar solution. So what we were given was an 8.6 molar solution. Is it? Oh gosh, it would. Sorry. Yeah. Yeah. When we sig fig out, it'd be 4.7. When we compare that to the solution we've got, is the solution we have more concentrated than that or less? It's a lot more. So this 8.6 is either supersaturated if everything is dissolved in it, or if the other possibility is it was an 8.6 molar solution, it was at some temperature where we could hold all that precipitate, and at 10 degrees, it's clearly, stuff may have fallen out of it. We may have precipitate in it. So it's definitely more than saturated. So It's either saturated with chunks in the bottom or it's supersaturated. And you could clarify that on a question like that on a test. You could say, supersaturated if everything is still dissolved. I think it violates the physical laws of the universe to have something that's like twice the molar concentration of a saturated solution. I don't think you could get that to happen, but there are probably some conditions under which you could. Does that help? Okay. And I think that's the simpler, more elegant way to do it. And that props go to a student in my other class who was like, I think my way was easier. I think you're right. Okay, let's go to number 7. Okay, so we're going to do number 7. Number 7, I like the ones like numbers 6 and 7 because these are the actual kind of things that you have to do in a lab setting. So we're told that you have to have 75 grams of calcium chloride and it's in solution and you need it to react with lead carbonate according to the reaction above. The only calcium chloride available to you is a bottle of 0.10 molar calcium chloride. What volume of that solution do you need? So, do you need the equation that's above the question? No, it's a red herring. It's there to distract. So you don't need to use it for this. When you're doing these kind of problems, these are like the gas law, where there are always two things you can do. You can start off with the molarity equation, or you can start off with a factor label. Okay? And here we're given a mass. We're asked to solve, eventually, for volume. So we have molarity. Do we have everything we need to solve for volume? No, we need moles, which means to get moles we have to start with our factor label. So we're given 75.0 grams of the calcium chloride, and we know that the molar mass of calcium chloride is 110.98 grams per mole. So we get 0.675797 blah 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 moles of calcium chloride. At this point, do we have enough information? Yep. And I know I mentioned this to a couple of you yesterday. I'm going to say it one more time. I get kids who have strong math skills. The students I have generally are pretty good at math. You have to be academic math track to take this. That's the prereq. You guys are smart cookies. Of all the smart cookies I get, in both chemistry and physics, 3-part algebra. You've been doing algebra since the 8th grade. You know your algebra. 50% of students will get solving for something in the denominator wrong 50% of the time. It's simple, it's stupid, but it's a great way to trip over your feet. So, I trip over my feet unless I do it the long way. I pretty much always do this. Multiply both sides by that. I have Lm equals moles. Then I can divide both sides by molarity. And then I have my solution. Because I screw it up too. So do your algebra. Do your algebra. Okay, with that, all we need to do is plug in our 0.675 blah 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 blah. And the molarity is 0.10 molar. So we get a whopping 6.7579, etc. liters of solution. With sig figs, we would say the answer to this is 6.8 liters of this solution. That is a lot of calcium chloride solution. That's 3.5 pop bottles. To put 2 liters in perspective. So 3.5 pop bottles full of calcium chloride solution. You're clearly doing sort of industrial grade chemistry. Sig figs. For this one, you would get them from the molarity, because the molarity is 0.10, so that has 2 sig figs. Don't forget that trailing 0 is significant.
Is the 0 in front and 0
No, 0 in front is not significant. Leading zeros are never significant. Zeros on the end are significant if they're behind the decimal.
So we always go with the
Least amount of sig figs, yes. And the question that came up in the other class that was a good one is, when you've got a chart, like the solubility chart, do you take sig figs from the chart? And you have to. It's not a conversion factor, it's a number you're getting for calculation. We have to assume that those were only measured to that degree of significance. So, Oh, you know what? Maybe I got the sig figs wrong on one of these based on that. Or no, it's different on the quiz. Okay, never mind. So yeah, you do have to pay attention to the sig figs, and the chart numbers from the chart do count. Okay, and the other one people want to do, we're going to do number 1. So this is number 1. You're given a saturated solution of iron 2 bromide at 20. What's the molarity of the solution? Do you have to know how much solution you have there to get the molarity? The fact that I'm asking you might make some of you think, no? You don't. You can do that without knowing how much of the solution, without knowing what volume of solution you've got. You remember percent compositions where I said something is 88% this and 11% this, and you made a magical 100-gram sample? We basically do the same thing here. We make sort of an imaginary 100 milliliter sample, and from that we can figure out molarity without having to know how much solution we've got. So, saturated solution of iron 2 bromide at 20, what's the molarity? Well, let's imagine that we had 100 grams of water at 20. How much iron 2 bromide could that hold? How much could it dissolve? Chart. Yeah, 124 grams of the iron 2 bromide. Okay. Well, so if we had that, how many moles of iron 2 bromide is that? So iron 2 bromide is kind of heavy, 215.65 grams of iron 2 bromide in 1 mole. So we have 0.5700, etc. moles of iron 2 bromide. And that's in how much solution? And again, we've got that same flaw where we're claiming that the whole volume of the solution is the volume of the water. We know it would actually be a little bit bigger volume, but we're going to go ahead and go with it. So if we take our molarity equation, we have the number of moles. We said this was in about 100 milliliters, so 0.1 liters, 0.57500 moles. I lost my 1. Okay. What's the molarity of that solution? .750057, etc. molar. And what are our sig figs? And the problem you were given, you had 500.0 milliliters of water. If you didn't have that, if you didn't have a volume to work with, you would have to take your sig figs from the chart. So what number in the numbers that you've got there would govern your sig figs?
500.0.
Well, but we don't have that in this, remember? So if you scratch out that volume, if you're not dealing with the 500, the 124 is going to control your sig fig. So we can have 3. So this would be a 5.75 molar solution.
I don't really know what I did.
Okay, other questions, comments? Yeah, and for anybody who's confused, this is only if you don't have a volume. If you have a volume, you use the volume you've got. So, questions, comments, cookies, quizzical looks. Okay. We'll just pick up with questions from the quiz right on the same recording. So you need 20 grams of barium nitrate in solution. You're reacting according to a reaction. It doesn't matter what the reaction is. All you have in the lab is 0.25 molar barium nitrate solution. How much of this solution do you need? So remember, there are 2 things we can start with. We can start with the molarity equation, or we can start with a factor label that's somehow going to connect moles and grams. In this case, we are given a mass in grams, and we are given a molarity. What we're being asked to solve for eventually is a volume. So we have molarity We'd like to have moles so that we could solve for volume. Since we have a mass, we can start with that. So 20 grams barium nitrate. And barium nitrate, she is some heavy stuff. She is quite the compound. So molar mass of 261.35 grams of barium nitrate. 2, yeah, in 1 mole. And that gives you 0.076525, blah, blah, blah. So we've got a tiny, tiny, tiny little number of moles that's actually needed. If we go up and we solve for L, multiply both sides by L, cancel those out, divide, oh no, then divide both sides by M, we get the number of liters, the volume is equal to moles divided by molarity. L equals 0.07652 blah 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 divided by, that is a 0.25 molar solution. So we get a volume of 0.306102 blah 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 liters. And with sig figs, we can have 2 sig figs. Get rid of that. We end up with 0.31 liters of solution needed. So that's, 310 milliliters of solution. So you're filling up an Erlenmeyer flask with solution. Good? That's it. Homework due tomorrow, 5:20, and test Thursday. So happy travels, kids.